Okay. So we discussed about this particular option, which was the discussed last option for the cogeneration, where we have found out that the am I audible and the precise slide is visible?
Yes, sir.
Okay. Good. So where it is interestingly another extreme of the cogeneration example, where the entire utility output was in the form of heat, though there was some at intermediate stage, though there was some power developed, but that power has been fully consumed for heat transfer from low temperature to high temperature, and effectively the total power output obtained is at two different temperatures. One is from the turbine exhaust, another is by the heat pump. And this particular system is a rather specific, typical, special system, but it was not typical special system, I should call it, in a sense of the space heating purpose for the cold countries, where the amount of heat required is high, but that's at a low temperature. I'm repeatedly reminding you during the heating purpose that the heat is always associated with its corresponding temperature at which it happens. And interestingly, if the same quantity of heat is required at a comparatively lower temperature, then that entire handling and the thermodynamically that is much easier. I'm not referring to thermodynamic route just because in this class there is a mixed group who have not studied the full thermodynamics course. But from the common sense also, it's quite obvious that the low temperature heat quantity, if it increases, then it's not that difficult. But quality of heat is determined by the temperature, which is obviously higher the temperature, higher the quality, and obviously it's costlier to supply also. Anyway, so from this cogeneration schemes, you have a basic idea. Again, I'm telling that even current research publications, journal research publications can be happen and can be done on the basis of innovative cogeneration scheme generation. So that it's not that whatever I have shown is the end of the cogeneration scheme. So cogeneration scheme development is still a part of active research at the highest level, with different new energy systems are coming up, power generation systems, heating systems, and combining them together in an effective way to get a better efficiency and sustainable system design is still a very active area of research, both for the industry and for academic development too. So with this, as with the limited time, I'm going into now cogeneration performance assessment. So what is the performance criteria of cogeneration plant? Try to understand the problem at first. I will give some dictations later. What is the situation when we try to assess the performance of a power plant? The power plant performance assessment is very straightforward, because what any performance, the best possible performance, or commonly, I should not call it best, the commonly available performance indicator is the efficiency. An efficiency of any device and service is defined as very straightforward: desired output, what you want to have from that system or device, by the required input. For that, what you need to give it. So in power plant, with respect to the actual desired output is the power output. So power output is in the numerator, and in the denominator, what is the required direct input for that is the energy input through the fuel. So efficiency power plant is pretty simple and straightforward. That power output divided by the heat input rate. But now, if you want to evaluate a cogeneration plant, then what is the problem arising? The problem arising, it has got two utility outputs. If it is honestly speaking, the true cogeneration plant means not the limiting cases of without having any power or without having any heat. If both are present, then what is the situation is, any of the utility output may be larger, another may be smaller. That means there can be different combinations of these two. For example, say you have got 40 unit of heat and 60 unit of power. So the total, if we just simply add up, because the heat and power both can be expressed in the same unit, kilowatt in SI, or other kilojoule in total quantity, and rate is in kilowatt. That means kilojoule per second. Now, if you simply add up, so 100 unit of total, and their unit is same, means they both are energy forms. I mean, different forms of the same, some energy. So you can simply add up and you get 60 plus 40, 100 unit of energy output you are getting from the cogeneration system. And both are useful for you. That's why you were adding up these two. And then if for that you need to give, say, overall energy input through fuel as 200 unit, then it becomes the denominator by numerator comes as to be numerator by denominator, comes to be 50%. Now, if this 40 and 60 mutually changes, means instead of 40, the other quantity becomes the 60, and the okay. That means the two utility output to handle the difficult part that comes up, whether they are of simply added up utility output or not. Any input from the class regarding this issue, then I will go to the actual small dictation or introductory part. Is the problem clear, whatever I'm telling? For one utility output system, your efficiency or performance indicator is straightforward. Desired output by required input. But if multiple utility output happens, then one simple way is just simply add them up. If they are in the same unit, then only you can add it up. In some cases, they may not be in the same unit, then the difficulty becomes even more. Anyway, so if you can simply add up these two units, then you can get one simplest possible definition. But within these two units, if you add up, the problem is one of the units, both together may make 100, say 40-60 or 60-40. Means I'm telling initially power and then utility heat. So obviously the total unit remaining 100 with the same calorific input through the fuel. Still, in that case, can we just assume that these two power plants are equally efficient, these two cogeneration plants are equally efficient?
Sir, when we will add the heat and work, that heat will be of all the heat, means utility heat and waste heat, all will be added, or only the utility heat will
No,
be added?
no, don't confuse with heat and waste heat, because waste heat was something that's defined specifically from the system process itself. That means process was actually desiring something else, but as a byproduct, there was some waste heat. Rather, if you cannot use it, that will be wasted. But here in cogeneration system, it can happen that from waste heat also you can make the cogeneration system. But that doesn't mean, because whenever you are getting the output as heat, whatever may be the source, we are not concerned. That may come from fuel. If it doesn't come from the fuel required input from waste heat, then obviously the corresponding fuel input will be zero, because that for that you have not added up any fuel. Fuel has been added up for another process. Got it? Anything else? So let's go to the first example. Now, let me give one preamble introductory note, then it will be better for understanding. Just write down. In cogeneration plant, in cogeneration, or alternately that is called combined heat and power, CHP, both are synonymous. In cogeneration or CHP plant, utility outputs are both power and utility heat. Full stop. In a fossil fuel based cogeneration, comma, these two utility outputs are obtained through some energy input of the fossil fuels. Using its calorific value. Using its calorific value. Full stop. The efficiency calculation, the efficiency বলো না, the performance indicator, the efficiency পরে আসবে, the performance indicator of a cogeneration plant is more complicated than a single utility system within bracket, say power plant, because both utility outputs may not be of same quality and hence not only their quantitative outputs but also quality value of each of these outputs must be included in cogeneration performance assessment. Full stop. Hence, performance indicator of cogeneration is of several types with corresponding limitations. Okay, so I have given an introduction that what is the problem or the difficulty with the cogeneration performance indicator vis-a-vis power plant. Because in power plant, utility output is only power, required input is the energy input rate through the fuel. So obviously it's straightforward. But in cogeneration, being two utility outputs, both power and the utility heat, so the quantity of each of these utilities cannot be simply added because there is some quality associated with those. So obviously there are different definitions of this performance assessment. Now I will discuss those things. And you will find out each one of them has its own limitations and little bit improvement also. So let's start with the first one. The first one is a very crude one, and it's a wrong one, I must say. But industry have used this particular definition for a long time. And in fact, when I was in my early part of career, I was a little bit confused how this can be an accepted parameter, because it is not, it is rather violating the basic principle of thermodynamics. Why? Just look into the expression. What is this? Because this was industry always looks for a simpler definitions which solves its purpose. That's a good idea. But if the simple things become accurate, nothing excellent like that. But if something is a simple thing becomes rather erroneous, then it is equally misleading. So, what is the expression that long term the cogeneration plants have used is energy utilization factor. The full term is the energy utilization factor. In short, they are calling it EUF. Obviously, you understand this is a term rather the similar to the term efficiency, because they are not using the term efficiency because it's not a single utility system. Direct desired output by required input cannot be done. So instead, they have coined a different term, energy utilization factor, EUF, which is defined as the ratio of two quantities. F is the required energy input through fuel. Obviously, this is the actually input required. That is okay, fine. Denominator, there is no confusion. What should be the denominator? Because you have added up some fuel to get these two utility outputs. But in the numerator, you have simply added up how much work output you have got. Work means obviously not with respect to per unit time, the total they have considered, and how much utility heat you have got. So summing up these two divided by the fuel input F is no doubt very simple. But the Q and W, adding up these two is the blunder mistake, because these are not of same quality. So just write down a little bit. Though energy utilization factor, though energy, you can write in short, though energy utilization factor or EUF is a simple expression and easy to calculate, it is misleading, because heat and work are not of same quality. Work is a higher quality energy than heat, thermodynamically. Thermodynamically. That means according to thermodynamics. Full stop. This is obvious as unit price of electricity is also higher than unit price of utility heat in market. Hence, adding up work output and heat output without considering the quality difference between these two is a misleading definition of performance indicator and hence not acceptable. I can tell you that in industry, because I'm next week only, I'm going to rather give a talk in industry in Haldia under Bengal Chamber on energy conservation itself only. I will just try to project these things in industry to the industry people also, because this is something wrong. Still, industry use it in some applications, but I should mention it that never go for this assessment because this is a misleading assessment. Anyway, so you can understand now though that from the but this is was the previously the single performance indicator used in general in the industry. But now, obviously, the better indicators have come up. If we compare, then we can understand the limitations of the previous one. The next one is the value weighted energy utilization factor. Follow the terminology. Previously, it was energy utilization factor only, and now it is value weighted. What do you mean by value weighted? If in a multiple outputs, the value or quality of those outputs are different, then you can add some weight factors. And you know the definition of weighted average. There is one is the arithmetic average, directly adding up the quantity divided by the number of the quantities. But if you want to give some different weightages, then obviously according to their weightages, they will be multiplied by the weightage term and then you have to add up. So, what is the modified improved definition of the flat energy utilization factor? Is the value weighted energy utilization factor. Look into the definition what they have done. This is the the expression is EUF suffix VW. VW means value weighted. It is equal to YE into W. What is YE? YE is the sale value of electrical power in the market. In the market, if you just want to get a connections at your home, so there is per unit electricity charge. Find out what is that charge, and that is the YE. Similarly, it is not required in our case because, but in our country, it may be required in industries, but not in. Just 1 minute. শুভ,
হ্যাঁ স্যার।
তোমরা ওই এলসিএ ডিসকাশনটা আজকে করবে আমি শুনেছি।
হ্যাঁ হ্যাঁ এলসি ডিসকাশনটা হলো এখনই।
আচ্ছা, আমি এখন ক্লাসে আছি 9:30 অবধি।
আচ্ছা আচ্ছা ঠিক আছে।
আমি ক্লাসের পরে তোমার সাথে কথা বলছি। আমাকে বলেছিল সায়ন আজকে তোমাদের হবে। ওকে
হ্যাঁ হ্যাঁ ওকে
okay. So now the useful heat cell value we don't understand regularly at in the domestic applications, but in cold countries, as I have mentioned, wherever there is district heating system, which I explained to you also during cogeneration system, that in hot water from the local power plant units is rotated through or circulated through different rooms, and then heating is done using some suitable heat exchanger and returned back to the boiler for reheating. So obviously you have to pay for heating units like electricity per unit charge in cold countries just to keep your room heated. That is required absolutely, otherwise you cannot live in that room. So there is specified sale value of useful heat is there, but in industry I mean, as we don't need the room heating in that sort of thing, we don't have that experience. But in industry, in our countries or tropical countries also, they need the utility heating for at a particular temperature for their process heating part. And that utility heating part, actually, most of the industries, their requirement, they develop their own system, but that has got a running cost, installation cost. Based on that, they can find out how much is the unit cost coming up. In some small industries, I know, in a what is called the industrial ecology system, where the different industries are located on a surrounding central heating system, where the central heating unit supplies the required steam at different pressures to those units. There, that central distribution unit, they charge for providing heating to each of these units. So obviously, why I'm explaining these things is that in some way you can calculate this YH, what is the sale value of useful heat. Unit is same, dollar per kilowatt hour. I have put it in dollar just because of dollar has got the universal acceptance. And Z is the price of fuel. So now see, in this previously EUF, what happened actually? You have directly taken the energy quantity in the utility output form. But here, you have not considered the energy quantity only. That has been multiplied by its corresponding market value or market price. So what has happened? You have given different weightage to unit energy value according to their market price. Now, what is the general principle of market? If it is a higher quality thing, price is more. And that is obvious also in the expression, or rather from your general understanding, that electricity price all over the world is always higher than this heating price, heating per unit price. Why? Because the costing of per unit price heating generation, or rather delivering per unit heating, is much lower than the electricity, because electricity needs a full conversion from heat to work. The equipment involved may be turbine, boilers, and itself a comprehensive power plant. So, and there is a effective efficiency also, and which is pretty low, 30 to 40%. That means around 70% of heat is lost in a power plant. So the issue is the work production or electricity production or power production per unit involves much cost, and so obviously market price is also more. And that is actually the underlying thermodynamic sense. Why the market price is more, that is also obvious. Why it is thermodynamically also, those who have studied thermodynamics, they can correlate that work is considered to be a higher grade of energy than heat. Interestingly, this higher grade and lower grade, just to make you an analogy for better understanding, I can give you one example. Though they are in same unit, they may not be always equivalent in a sense. When you go abroad, we convert our Indian rupee from the currency converter in our country to either dollar, or currently euro is also good. Why we need to convert it? Because if you go with some several crores of rupees of Indian currency to another country, nobody will accept it and get you converted. You have to get it converted at your own country, because your own country value your own currency. But internationally, previously only $1, but now currently dollar and euro both has been accepted as the international conversion currency. That means you have to convert your national currency into your corresponding international currency, dollar or euro, within your own country, because that will makes the actually balance of the so-called, the foreign currency reserve is a very important indicator for the economic development. I cannot go into those aspects actually, but you being all adult, you have heard about it most probably. So obviously, if you just convert your Indian currency into dollar, automatically your earned dollar from the other countries is also decreasing simultaneously. So government has certain restrictions also of converting Indian currency to dollar when you are going up. If you earn dollar from outside, government will always very much welcome you, because if you bring dollar to Indian country and then reconverted it to Indian currency, then that goes into the dollar goes into the currency reserve of the country. But the net essence is the Indian currency or any other currency than dollar and euro, they have got their value within their own country only, but they have an equivalence if you get it converted in your own country. But dollar and euro has got international acceptance both in those countries where they use, or any people from Europe, they are coming to India. If they want to convert their euro into Indian currency, any currency converter will do it. But there are certain regulations because you need to show your passport, visa, etc. Why I'm giving this example? Just because the value and the quality, these two are different. Indian currency or other currency has also got some value, but they cannot be converted at your own sweet will anywhere. So dollar and euro are a different quality economic unit, which is equivalent to our power. But utility heat is a lower quality energy which has got its lower category value like Indian currency or other currencies. So it's just a comparison between the dollar, euro, and the other currencies you can feel about. Though each has value, but one is high grade, universally acceptable, and another is low grade. Okay, so with this, if you look into this expression, you can find out that the cell value of electrical power and cell value of useful heat, these two, if you multiply in the expression of the utility energy utilization factor of value added, that means value addition consideration is included, then automatically the limitations of the previous expression where no difference of the utility heat and power has been considered is removed. So obviously this is a better acceptable expression for the than the previous one. So just in summary, I can write one sentence. EUF suffix VW, that means value weighted energy utilization factor. EUF suffix VW considers the difference in power and utility heat by multiplying their magnitude with respective cell values. Full stop. This implicitly includes the concept of thermodynamic quality difference of these two energy utilities. Thermodynamic quality difference of these two energy utilities. Okay, so we have at least considered two. One is just flatly, it has not considered the quality difference and flatly added up. And then another has considered this their quality difference through a particular specific objective of assigning their corresponding cell values. At least that is implicitly their quality is also included in the expression, because cell value of electricity is always higher than the cell value of the utility heat. Now I'm coming to a little bit more complicated apparently, but little bit better expression for the so-called cogeneration schemes. What is that? This name is fuel energy savings ratio, FESR. Why? I mean, just at first identify what is the process of expression of this definition. And then we will go into the discussion of how it improves the, or rather, in what sense it is better definition than the earlier. So it has defined a fuel energy savings by delta F. What is that delta F? If you don't go through a cogeneration, why you have gone for the cogeneration, or why you recommend the cogeneration? Because you need two utility outputs. That is, one is power, another is the utility heat, and they both can be delivered by through separate entities. Say the power can be generated by a power plant, and the utility heat, whatever is required, can be generated by a suitable boiler installation. So in that case, these two separate utility outputs would not be combined together. They would be standalone. We call it standalone utility delivery units. Now, the cogeneration from the energy conservation viewpoint will be preferred if and only if combining these two utility outputs in a single system helps you in saving the fuel. So, in saving the fuel, from that definition, how much fuel you can save, that is the most important concern of the so-called cogeneration system. So the definition of delta F is coming out to be QU divided by eta BH. What is the eta BH? Heat only boiler efficiency. If you don't go for cogeneration, then what would you do? You would use a boiler, best possible boiler available in the market, say. Then that efficiency is eta BH. So you have to install that boiler and generate the hot water and steam as required, the temperature of that heating requirement. So you can just make an effective fuel input will be how much? If QU is the utility heat requirement, then eta BH will be divided by eta BH will be the required energy input through the fuel. Okay. Similarly, for the work output W, correspondingly efficiency is eta 0 W, overall efficiency of power generation by a standard power plant available in the market. So these two utility outputs you have separately generated, and adding up these two means you have certain energy requirement. You have the same energy requirement has been fulfilled by two standalone utility heat supply boiler and a power generation or power plant. So minus F is what? F is that fuel which is actually required for the cogeneration purpose. Now, if the first term is not more, that means the fuel energy required for standalone systems is not more, then you don't save any fuel through cogeneration. So I'm assuming that that cogeneration will be only accepted if this expression of delta F is positive, because the first quantity is expressing the standalone system generation and minus the actual fuel that is used in the cogeneration system. So the delta F, once you have calculated, that is the fuel savings, then go to the definition of the next after hence. FESR is equal to delta F divided by the same quantity that is calculated as the first term of the delta F. The first term of the delta F is what? That is the reference fuel energy requirement. What is that reference? Reference is if we could have generated, rather than cogeneration, separate standalone heating system and separate standalone power generation. So by combining these two in a cogeneration, you have to have some incentives of saving of fuel. Otherwise, you don't go for cogeneration because that is a complicated system. So obviously, the delta F, if it is positive, then only you go for cogeneration. And the FESR is defined as delta F is the amount of fuel saving divided by the corresponding reference fuel. Reference fuel is for the separate generations of the heating and the power. That is coming out to be 1 minus within bracket F by F reference. F reference means reference fuel that is required for separate generations or standalone generations of the same work and useful heat. Is it clear? Any queries on this particular expression? Okay. So if not, then just write a brief, concluding remarks on this FESR. In industrial application, saving of fuel through cogeneration than conventional supply of the utilities is the objective of energy conservation. Fuel energy saving, FESR লেখো, fuel energy saving is a longer word. FESR definition is based on that particular objective of saving of fuel through cogeneration. First off, in FESR definition, reference fuel requirement is calculated by using standard separate or standalone systems for these two utility outputs. And is denoted by F suffix ref or EF. The actual fuel energy required within bracket F must be lesser than this reference fuel for cogeneration to be useful. Full stop. Hence, FESR directly indicates the percentage of fuel saving through the cogeneration system. Which provides a straightforward performance indicator for the industry. Okay, so what I just want to mean, out of these three definitions, the first one is absolutely wrong. I will in fact promote it next week also in the energy conservation workshop in the industry. If they use it still, I will completely discard that. But the second one is a better one in a sense that it takes the thermodynamic concept of quality difference of the work and heat. But the third one gives an even better definition from the viewpoint that the industry is rather more interested with how much fuel saving actually in percentage they can have, and that value is directly given here, because efficiency always has got some implied sense of the technology understanding. But whenever you are talking about the fuel saving directly in a definition, then that gives a better meaning or easier acceptable definition for the industry. For example, we can express the thermal efficiency of a IC engine, but in road condition, the people express the term with respect to how much mileage does it give per liter of petrol, because that is a more practical expression. So like FESR and the value-weighted energy utilization factor, both are giving similar performance indicator by considering the quality value of both heat and the utility heat, both heat and the power. I mean, but still, these two are in from different approach. One is still keeping in the formations, in the definitions of the efficiency term, and another is rather not including the efficiency concept. They are expressing with respect to percentage saving of the fuel in this process. So any queries up to this? No. Okay, then I can go to the next definition. The next definition is the artificial thermal efficiency. Another interesting, rather it came from academic viewpoint, and industry also partially accepted it in a sense. It's a good idea. Whenever you have the two utility outputs, then you can define it in one sense. One is the main output, another is the auxiliary output. That means byproduct. So if a cogeneration, it has got two utility outputs. One is the work, another is the utility heat. So if you consider that work is the main output, then the auxiliary output is the utility heat. Now, the auxiliary output, whatever you have got it, that if you just subtract from the fuel energy required, corresponding fuel energy required, then obviously the expression will be considered as an efficiency expression, because that becomes a corresponding single utility output definition. But the filling of cogeneration is included in the denominator by subtracting the fuel energy input into the system, because you are getting another auxiliary output in the form of heat, utility heat. So in the expression, if you look into that, that's why it is an efficiency expression, but artificial, not natural efficiency expression. So the terminology is artificial thermal efficiency. So what is the expression is, if your work output is W, then you keep the desired output as the single utility output. You don't add up any heat expression on the numerator part. Then what is your definitions of, because you have to consider the heat output also, though as an auxiliary output. So So you divide Q by eta B. Eta B means that heat only boiler efficiency. So what is the meaning of Q by eta B? How much fuel energy required for that heat output that you are having in the cogeneration system? So Q by eta B is the fuel amount that is required if you want to generate in a separate utility system by heat only system or heat only boiler. Subtract that from the fuel, obviously, because otherwise you would require that additional fuel for additionally in addition to power plant, another heat utility boiler would be required. So subtracting that Q by eta B from the F in the denominator, effectively it has become an efficiency expression only with corresponding lesser fuel energy input for this particular power plant. So this is an interesting definition because the cogeneration, two utility outputs, has been equivalently converted into one power output with some artificial subtraction of the contribution of utility heat as a form of subtraction in the denominator part from the fuel energy input. So from these definitions is a summary. I just write down one sentence, just write down eta A, that means the artificial thermal efficiency. Eta A basically considers cogeneration as a power plant and utility heat as its auxiliary output, full stop. Hence, fuel energy required.
Sir, sir, can you repeat the first line?
Shobanash.
Eta A considers a cogeneration.
কোজেনারেশন এটা অন্য কেউ বলে দেবে? আমি তো মুখস্থ থেকে বলে যাই, মানে নিজের থেকে বলে যাই আর কি, মুখস্থ বলে কিছু নেই। একটু বলে দাও না অন্য কেউ যেটা শুনেছো, নেটওয়ার্কে প্রবলেম হয়েছে।
Cogeneration as a power plant and utility heat as its auxiliary output. Hence, fuel energy required.
Okay.
কমপ্লিট, ওকে ফাইন। হ্যাঁ, ওকে, আবার লাস্ট কি বললাম আমি? হেন্স না?
Hence, fuel energy required.
Hence, fuel energy required for this artificial thermal efficiency is lesser as corresponding fuel energy required for utility heat is subtracted at the denominator. Okay, I don't think much of discussions is required on that, but obviously from academic viewpoint we can have a lot of, rather comparative studies out of these four definitions. And again, I'm reminding that first definition should be ruled out completely because this is completely erroneous. But unfortunately, I must admit that industry, even currently, I'm not very sure because in that interactions I will also raise that issue. industry actually use that energy utilization factor for a long time. And in some of the cases, the cogeneration plant efficiency has been expressed as more than 95, 96%, because that's a heat, mostly heat, very little amount of power. So it's a very misleading definition, because people become rather unnecessarily misled by some 95% efficiency sort of cogeneration. It should not be. But in this other three definitions of B, C, and D, they are quite rational of considering the quality difference between the heat and work. I hope I could give the message of the cogeneration performance indicator assessment and at least some parameters introduction. And there are even more. Even today also there are some new definitions are coming out for the cogeneration performance assessment, and with some new dimensions. And that also you can do, because some of the definitions come from the thermodynamic exergy analysis and other things. Unfortunately, those things I cannot cover here, though I discuss those things a little bit in the mechanical courses. Anyway, so with this, I feel that if you don't have any more queries, the cogeneration part for your examination is over, because there are many things I can go on talking, but that should not be. I have to stop somewhere. So in cogeneration, in a summary, if I tell you, I mean, we have given an example of cogeneration as a energy cascading option, which has been mentioned in the very beginning of the energy conservation class as one of the options of the energy conservation. Cascading means you are adding up energy utilities for better efficiency. And in fact, one of your friend today has asked about the questions difference between energy nexus and energy cascading. That, though it's not part of your discussions, but I'm just giving you the idea. Sometimes this adding of certain energy utilities add up to burden. That means increasing more energy liability. For example, food, water, energy nexus, where the food production itself consumes some lot of water and energy itself, or water energy nexus, water supply process of human consumption takes a lot of energy in the pumping system, in the purification process, etc. So these are not cascading, these are nexus effect. But the cascading effect is where adding up to energy utilities will give you better energy conservation. And that's the definitions of the cogeneration. And starting from that, we have discussed some of the basic cogeneration schemes. Most important is the back pressure and the extraction turbine sort of example, where one is used for low heating but at higher temperature preferred, and then another is used for large heating amount but at a lower temperature. Then we have come up with some definitions, a very special case where the entire cogeneration system is converted into a heat only system, and though intermediate power is delivered, that is completely used for a heat pump, and that is very much important for the space heating purpose, where large amount of heating is required at a lower temperature. Then we have entered into the so-called different performance indicators of the cogeneration, and in that different performance indicators of the cogenerations, we have found out that there is a relative improvement in the subsequent definitions, and also the different dimensions has been approached for the performance indicator assessment. The first one is the wrong one, and the second, third, fourth, they have a different approach. One has taken the sell value of the market or the market price. The second one has taken, the third one has taken the fuel saving aspect, and the fourth one has taken as if the utility is an auxiliary output. So I've got some revenue return from the fuel saving part. So all these three are relevant, but they have got their different degree of rather the acceptance, or rather different degree of advantages. But undoubtedly, these three all are better than the first one. Over. So I think the cogeneration part is over, if you don't have any queries. Now I'm going to the energy storage, little bit exposure. I'm not going to make entire details possible, how much I cover in other courses, but here I want to give you some general idea about energy storage. Now the question is, why the energy storage is at all required for energy conservation? Why we study energy storage at all under the energy conservation? Any idea?
Sir, because it is one of the measures, like in high demand time, we need better storage facilities.
Yeah, you have come to the answer, but the expression is not rather proper. The way is, you have rightly identified that the demand and supply, these two always doesn't match. And one underlying sense is there, because your system performance efficiency, I mean system efficiency or performance, depends on how much capacity you are delivering, whether it is a power plant or it a boiler, or it may be some other energy utilities. So if you can run a device at its design condition. Design conditions means at which it will have its maximum efficiency or performance. So you can have the best efficiency means best fuel performance. But if the demand decreases, then what do you do with this excess? So this excess becomes a problem for any device if the demand fluctuates. But if the demand remains steady, you go on generating at the steady condition and your plant efficiency can be set into design value, then obviously you will get the best performance, best fuel performance, or rather best minimum required fuel energy. But as your friend has mentioned, that with fluctuations of the demand, if the supply has to vary, then what is the option? One thing is we can do, we can adjust the supply also according to demand. That means we are running the supply unit at a lower efficiency, and so you are consuming more fuel, energy conservation is violated. But if you can run at a constant efficiency, then whenever there is demand is less, if you have a storage, that generated energy is stored, and whenever that demand is even more than the standard generations of the utility output, then you just release that energy to the system to compensate that additional demand. So as if the gap between demand and energy is compensated by an useful energy storage system. Then just write down this brief note, because you don't have any textbook. That's the problem of this subject. Just write down the efficiency of any energy system. The efficiency of any energy system depends on its operation at its designed condition, at its designed condition, full stop. At that designed condition, efficiency of the system is maximum. Hence, any deviation of operation of an energy system from that designed condition consumes more fuel. For same utility output.
For same.
Utility output.
Okay.
Energy storage, next sentence, energy storage provides the buffer, BUFF, buffer, between the buffer between the demand and supply to help operating the system at its designed condition. Okay, go to the next paragraph. In energy, in conventional energy conversion chain, not conservation, conversion. Fossil fuel energy or nuclear fuel energy, fossil fuel energy or nuclear fuel energy is converted to electricity through the heat to work conversion route. Full stop. In this conversion chain, energy storage opportunities are also there at each stage of the conversion. With different suitable technologies. Now, if we go into the conversion chain, where and how to store energy in energy flow chain. What is that flow chain? You just see. Initially, in conventional conversion chain, because the other energy, we call it unconventional energy, because the conventional energy always means fossil fuel based energy systems to your utility energy form. And utility energy form, as we have started with this particular course, this most desired secondary energy utility is basically the electricity. So obviously, the most basic input is the primary energy input, which is in the form of fuel. All of you know that from most basic input of primary energy to the most desired the most desired form of the secondary energy is the electricity. In between, there are different conversion chains. In this conversion chain from fossil fuel based energy up to the most desired secondary form of energy, electricity, there are different forms of energy, and each stage you will find out interesting possible options of storage, but obviously these are based on different technology. Now the corresponding storage, if it is a fuel, then why I'm telling the fuel level storage? Yes, that's the ultimate objective of the energy conservation. Because when you go for the fuel and the corresponding storage system can be, you can, if you buy any mechanism, if you can make some energy conservation measures, then what will effectively that will lead to a fuel saving, and that's the final, I mean, the ultimate objective or sole objective of the energy conservation, reducing fossil fuel consumption. So storage at the fuel level, if you can make by any energy conservation measure, your fuel will be stored in the form of chemical or nuclear fuel. Then the fuel gets converted through the combustion route into heat engine, so that you want to get this corresponding conversion of work. But when you burn the fuel, then the fuel doesn't remain in fuel. But if you can store fuel in the form of fuel, that's the best possible option. Because once you have burned the fuel, it has been converted into heat, and you can never get back the fuel from this heat, because this is an irreversible process. Those who know the thermodynamics, they know it very well. So if you can store fuel or save fuel, that's the best option, because after converting fuel into heat, you can never get back with that heat into fuel. It is an irreversible one-way conversion. So obviously the fuel saving, the first level of saving or highest level of saving is the best option. But after combustion, if it is converted into heat, and then also after giving the heat engine, you have certain excess to store, then obviously the heat engine can be, and that heat can be stored in different forms. In fact, this is not the exhaustive list, but I have given 2 options, and the second option has got 3 sub options. This is the heat storage is a very important challenge currently from the technological viewpoint. In internet searching, you can find out a lot of document, but obviously this can be those who are interested and want to work in this area. There's an active area of research of how you can make the heat storage. In fact, the heat availability at different occasions, locations, if you can make it some heat storage and release that heat whenever it is required again, then it is also a very good area of application. Usually in heat storage, we use either generation of superheated steam. That's one option. And you know the meaning of superheated steam, that means at that pressure above the saturation temperature. Then another option is the thermal storage. Generating superheated steam, the purpose generally becomes you can reconvert it into power also, because superheated steam is very much suitable for the power generation. But as a thermal storage, it can be sensible heating, in the latent heating, or both. That means combination of both two. You know the meaning of the sensible heating? Whenever you will store that heat, that will raise the corresponding storage medium temperature also. That's the sensible heating. In some of the cases, say the wax or some sort of similar material, what they do, the solid is getting converted into liquid. That means there is a latent heat addition, not temperature change or not much temperature change. So maximum amount is stored in the form of conversion of phase from the solid to the liquid. So that's the latent heat storage system, thermal storage. And in some cases, they are in the form of small capsules of latent heating and simultaneously outside a liquid media or base as the sensible heating media. So I'm just giving the examples and short discussions of these things just because each of these technologies is a very involved one, and mostly these are depending on the suitable material selection, because the selection of material matching with the requirement and matching with the temperature and the system requirement is the ultimate essence of this particular research area of heat storage. Anyway, so in the conversion chain from the fuel through the combustion to heat, we have the superheated steam, we have the thermal storage system, and thermal storage can be either sensible heating, latent heating, or combination of both. Then the heat engine is what it is doing. It is generating certain mechanical power which is given to the generator. And this will, in between, the heat engine is generating work or mechanical power to supplying to the generator. So if work is excess, what can you do? This is the intermediate storage options. These are the intermediate storage options at the work stage. You can store in the form of kinetic energy, you can store in the form of potential energy, you can store in the form of pressure energy. The kinetic energy example is the flywheel. I don't know whether you know it, because whenever to any fluctuating power delivery device, usually there is an attached large wheel of which the mass is more concentrated on the outside. in the form of a rim and small ribs, because it will have a higher moment of inertia. So the flywheel is a device which is basically a auxiliary power storage during the excess power delivery or mechanical work delivery by a heat engine. Then comes the potential energy storage is lifted water. Most probably you might have heard, many of you, in West Bengal, on top of Ajodhya Hills in Purulia, there is one pumped water storage system. What is the principle? Whenever you have excess electricity or excess mechanical power from anywhere, use that to run a pump and pump that water from the low level at the base of the hill of Ajodhya, because that's not very high hill. I mean, this is a very basically a low altitude sort of. It's not a mountain. It's basically some sort of hillocks. So you transfer that water from the low height up to the top of that particular small hill. Then, whenever power is required, use that potential energy of the water in a hydro power plant so that water will flow through a hydro turbine to compensate that power. This is called pumped water storage system, which is practically existing in West Bengal. We are lucky to, if you have an opportunity, you can see it. That's in Ajodhya, Purulia, Ajodhya Hills. Another option is the pressure storage system, that is the compressed air. Any excess work output can be stored in the form of raising the pressure of air stored in a pressure vessel. But this is obviously is a costly and rather little bit design specific thing, because any high pressure storage system has got a possibility of explosion. So you have to be very much careful of designing of that pressure vessel, because you can go on increasing the pressure inside the system to get more and more energy stored inside by gas pressure or compressed air pressure storage system. But unfortunately, if your storage system of the high pressure vessel is not properly designed, that may have a chance of accident. Anyway, so this is another way of storage system. And then from the generator, you get the electricity. If it happens that electricity itself is also excess somewhere, then currently this is the most challenging area of the energy storage. In electricity storage, there is no such large scale electricity storage system yet, and that creates that's as floated as the greatest challenge in the energy sector, I must admit, just to solve this renewable introductions and etc. Because unless we have a very large efficient electricity storage system, the full conversion of fossil fuel into the renewable energy will be seriously limited, because the renewable energies are available according to the wish of the nature, not according to the demand of the human being. So whenever it is available, say during summer we have a lot of sunshine. So if the solar energy during the summer can be stored to be delivered during monsoon season when the sunshine is pretty less, then obviously the overall energy that the sun gives us to the earth is quite good enough over the year. But unfortunately, that is during monsoon season, your energy requirement, human energy requirement, is not less than the summer period or winter period. So you have to make a storage system. If you have to make a balance of those the fluctuating renewable energy systems for your human consumption, obviously you have to make a balance between these two, and for that you need the proper electricity storage system. But currently there are two types of storage. One is the capacitance, that is based on the static charge, and obviously these are not much amount of storage cannot be done. The limited, because the capacitor size will become so big, it will not be practically possible. But capacitance is an option for small amount of electricity storage for a shorter period. And another is the electrochemical option, where a chemical reaction happens due to the flow of electricity in one particular direction, and the reverse reactions of the chemical reaction happens to release that electricity. So this is the principle of the so-called electrochemical batteries. Lead acid batteries, lithium ion batteries, whatever the batteries are there, they all operate on these electrochemical principles. But electricity storage on a larger scale, developing some new technologies, it will happen someday, because human invention strives always results into some good results. But this is the greatest challenge now in overall energy sector sustainability, because if you want to depend fully on renewable energy systems coming out of the entire fossil fuel regime, then energy storage at the electricity level must be very successful. So as we have rather covered our time, I can just, give. I don't think it is needed any discussions or other dictation sort of thing. You have, it's a pretty clear picture that the energy conversion chain from fuel through heat, work, and electricity at each level. This small discussions may be good enough, but maybe in the next class, if required, I will give some little bit. As I do it for next class, the last discussions of the previous class, I will just give touch on this issue. Any queries up to this? Then I will have the roll call.
Sir, is energy storage also done to recover the lost energy, means in the form of pollutants like carbon capture and storage is a new method of capturing carbon dioxide and storing it on the ground for future usage.
In fact, it's not. You don't confuse between these two. And interestingly, we also confuse sometimes. What you are asking about, carbon storage is coming from a different purpose. And carbon storage, these are all, named according to their utility objective function. Carbon storage is done to save the world from the so-called greenhouse effect.
Yes.
It needs certain energy for the carbon storage process itself. And in fact, large amount of energy, it is an example of a energy nexus problem, I can say, because carbon dioxide is produced from the energy sector, and to store the carbon of that carbon dioxide emitted from the power plants, you need energy. So it's basically energy nexus problem, another example of energy nexus problem. Now, what I'm just giving in response to your question, if you can have energy storage from any of these systems, like waste heat recovery is also a recovery, an utility of the waste heat. But if not required, don't go for storage. Why I'm telling if not required? Because storage means, apparently it looks a very good options of storage, but each of these storage systems has got its own inefficiency. Means no storage system is 100% efficient. Means if you convert with some electricity to electrochemical system in a battery, then battery will not deliver 100% whatever you just gave in input in the during the storage system. That means your mobile, even how much your mobile battery takes in during charging, it doesn't return back the same amount. There is a certain percentage. So any conversion chain is, the lesser the conversion chain we can make. Sorry, I have some throat problem. The lesser the conversion chain we can make in the energy conversion process, it's always better. So storage will be done if and only if it is required to make a better efficiency during the demand and supply gap. Unnecessarily storage is not recommended also, because storage will also cause certain inefficiencies. Is it clear?
Yes, sir.
Okay, any other queries?
Sir, can you repeat artificial thermal efficiency once?
Oh, but that's very difficult because you have taken the notes, no? You have taken the notes.
Yes, sir.
Now I'm explaining. Anyway, you asking means you are taking interest.
Yes, sir.
So artificial thermal efficiency, you just look into the philosophy itself. I'm going back to the slides again. As you were asking, that's good. At least the class is now responsive. Okay. This is the artificial thermal efficiency definition. So in artificial thermal efficiency, it's a thermal efficiency, but artificial. So what is thermal efficiency? Thermal efficiency is related to a power plant. To a power plant, what is the efficiency expression? Power output divided by the heat energy input rate, or rather work output by the power plant divided by the heat energy input. Now, it's in cogeneration, only power is not the only utility output. You have two utility outputs. One is the power, another is the utility heat. But you are as if assuming the cogeneration as a power plant only. So it's an artificial thing. And that's why corresponding performance indicator is not an efficiency, but an artificial thermal efficiency. Why? What you have done, in the denominator you see that the fuel energy required is not F. That's the total fuel energy required for the cogeneration system, out of which you have subtracted the corresponding fuel that would be required if it is not integrated in cogeneration systems, and you are trying to supply that fuel energy, trying to supply that heat energy from a separate standard standalone system. That means in this subtraction process in the denominator, F minus Q by eta B, what you have done? You have tried to convert the cogeneration system into an equivalent assumed power plant only, not no heat is there, only power plant. But the no heat is there is included in the denominator part, where the actual fuel energy required is little bit less, because if Q divided by eta B is subtracted from the F. That means in an efficiency expression, W by F, if the denominator amount decreases, fuel energy input decreases, automatically efficiency increases. So in cogeneration process, by considering it to an equivalent power plant, you have made a more efficiency or higher efficiency by subtracting the corresponding fuel energy input, which is really happening in the cogeneration process. Otherwise, that utility heat output would have been supplied through a standalone heating boiler. Is it clear?
Yes, sir. Yes.
Thank you. Please think over it, because the idea of you are mostly third year, fourth year student in the open elective course, there what happens actually, open electives, the concept is always you have to go through this, width of this subject, not the depth. I cannot, because all the students of different background in different years, I cannot bring all them to equally acceptable. So I'm just putting the things conceptually. But when you go to the industry, in fact, I will put to this WhatsApp group, the workshop, the Bengal Chamber. Bengal Chamber means it's a purely industry chamber. So they are organizing one workshop and they are inviting us for their presentation. That means industry needs it. And in fact, I was very happy that just 2 to 3 days back, actually, one of my last year mechanical student, he has got the job in, I forgot this company, anyway, the Ford Marshall company. So they have employed him into their energy conservation section of the industry, their unit. So he was just telling me he wants to sit and discuss. I'll be very happy for the students. I don't know, at least some of you maybe, joined to a company as an energy auditor. In some cases as energy auditor, in some cases as energy manager. So you will be responsible for the energy conservation aspects of the company. So when we teach the students, we are not concerned who will go to which industry. We give a general knowledge base. And then obviously the students, according to their placement, they learn more in the industry of that particular specific knowledge requirement. Okay, thank you. So make a roll call. Sheikh Wahmad Ali? No. Then Diptendu Gupta?
Present, sir.
Good. Then Shaunak Agarwal? No. Then Anubhav Shaha? No. Then Gitan Dash? No. Boibhav Agarwal? No. Piyal Bishwash?